Okay, so let's get started. Does anyone have a question?
Yeah, so in the homework, in the question about Carnot cycle and graphing it in ST, PT, and VT plane, we have asked us to state the equations for all the curves as well.
Yeah.
Could you elaborate a little more on what you are exactly looking for? Because I don't think I understand what we have to describe as equations for the curves for those.
Okay, that's a good point to get started for today's class. So what we have been talking about is, and by the way, I made some people co-hosts. If you could put in the people in the waiting room in the class, I mean, you guys are not using double factor. You should not be facing waiting room if you are using double factor. And it's very hard for me to let people in when I'm teaching. So thank you for your help. Okay, so we have been talking about the Carnot cycle, which in a pressure volume space looks like you start at a point, you do isothermal expansion, let's call it process 1 at a hot temperature. Then you do adiabatic. Then you do again isothermal cooling. And then you again do adiabatic. So this is process 2, which is adiabatic. Process 3 is isothermal at cold temperature, and process 4. So last time, before we did this, remember we derived an equation for this curve. Do you remember what that equation looked like, Sanjana?
Is it the delta S total is equal to?
No, we derived an equation connecting pressure with volume for the isothermal expansion of an ideal gas. It was something like PV to the power gamma is equal to constant, remember?
Oh yeah, okay, yes.
That's
So
the
we
type
did
of stuff you need to derive. Yeah.
Yeah, so we did something similar for T and V as well. So that's what you're looking for in all the spaces, right?
Yeah.
Okay, I get it. Thank you.
Yeah, no problem. There is a reason that problem has so many points, because you will see you will get stuck sooner or later, and then it's not too hard, but you might get stuck. Okay, so this is any more questions? Okay, so let's resume. So we are talking about a Carnot cycle. Why did we talk about a Carnot cycle? The whole idea was that if you have a heat engine that is taking heat from a system from a hot bath at a temperature TH, let's say you are taking the engine is taking some heat from this, which is modulus of QH. It is taking this heat to do some work. So there is a rotor that can be turned or something like that can happen. The work that you get out of is W, and some heat is getting dissipated to a cold source, which is at a temperature TC. So we said that the thermodynamic efficiency is going to be modulus of work that you can get out of the system divided by the modulus of heat that you actually took in. And intuitively, it makes sense. Well, mathematically, it makes sense. It cannot be negative because we have two moduli, but it cannot also be higher than 1. And this makes intuitive sense. In the homework, in the bonus problem, I want you to think very carefully what would happen if efficiency was more than 1 for a reversible or irreversible process. For a reversible process, it's kind of easier to show that it cannot be more than 1. For irreversible, you have to really think slightly harder. So this thing cannot be more than 1. Carnot's theorem says that actually you can write down a number for the maximum possible efficiency you can have in a river. So first of all, it's easy to show, and we did last time, that eta reversible is going to be more than equal to eta irreversible. The maximum, I mean, this is obvious because if you look at W, we know that W irreversible is less than equal to W reversible. A reversible process, you get more work out of the system. So this shows that reversible efficiency is going to be more than equal to irreversible efficiency. But Carnot's theorem goes one step further. It says all reversible engines operating between this hot source and the cold sink will have the same efficiency, which then becomes the maximum efficiency that you can attain. And that is given by eta max is equal to 1 minus Tc by Th. So what we did last time was to derive the efficiency for this Carnot process. We showed for a Carnot cycle we showed that efficiency is equal to 1 minus Tc by Th. Now we are going to go one step further and show that actually all reversible engines should have the same thermodynamic efficiency. If you have two possible engines, now we will show that it is not possible. By the way, last night in my dream or nightmare, whatever you want to call it, my fourth grade teacher showed up and told me my handwriting is really bad. It was it was a nightmare, and I couldn't do anything. I'm sorry. Yeah, it's not gonna change. It's terrible. That's why I write here in the front thing. If the handwriting is not clear, ask on Slack. Don't be shy. I know my handwriting is terrible. I could prepare notes nicely written, but then what's the fun? That I don't like teaching like that. It sucks. And you will also get bored if I did that. So now we will show that it is not possible to have two engines with different efficiencies running reversibly, because we already showed that reversible efficiency will be higher than irreversible efficiency. So now we can focus only on reversible processes. Between, B/W means between some hot source TH and cold sink TC. Okay, so now we are going to show this. So we will show this by what is known as proof by contradiction. Okay, we will show that, well, let's say it is possible to have two heat engines where both are working reversibly between a hot source and a cold sink, and one has higher efficiency than the other one. Okay, so let's say that engine A has higher efficiency than engine B. And we will show that this leads to a contradiction. Okay, so what we mean is eta A is more than eta B. Remember the definition of eta? Eta told us how much work you got out of the process divided by the amount of heat you sucked in from the hot source. So this is going to be WA divided by QHA, amount of heat you sucked in from the hot source. That is more than WB divided by the amount of heat the engine B sucked in from the hot source, right? So this is going to be true. Let's call this equation number 1. Now, WA is going to be QHA minus QCA, right? So let me draw a little diagram here so you remember. So for process A, you are doing WA work. You are taking QHA amount of heat and you are giving back QCA amount of heat to the cold sink. Okay, so you can see that the QHA plus, sorry, WA plus QCA must be equal to QHA. So the QHA, the heat that you sucked in from over here, in the blue thing that I just marked, has to go either to the QCA or to the WA. It has to go to one of these, right? So that's what we wrote over here. So this, let's call equation 2. And similarly for process B, WB is equal to QHB minus QCB. So right now we cannot do much. We are going to make one assumption. We are comparing two heat engines. Okay, so and pay attention to this point, because this is where students get confused. Right now we have to make one of two assumptions in order to compare things. Either we have to say that, let's say the amount of heat they are sucking from the hot source is the same. So either we have to assume that QHA is the same as QHB, and then we talk about the work done, or we assume that, let's say, the amount of heat they are dissipating to the cold source is the same, okay? So I want to repeat this. So in order to compare two engines, you have to, because all energies are, there, everything is relative. So we have to say, we will set QCA is equal to QCB, just for reference, just for a reference point. So we have two engines, both of them are taking some amount of heat from a hot source. They are sucking, they are dissipating this heat to the cold sink. And we want to show that they cannot be doing different amounts of work. Okay, so if you are giving out the same amount of heat to a cold sink, what happens in this case? Okay, so let's work with this. So in order to do this, first, let's put 2 and 3 in 1. So when we put 2 and 3 in 1, what do we get? We get QHA minus QCA divided by QHA and is equal to QHB minus QCB divided by QHB. Okay, so this part over here, QHA by QHA is equal to 1, QHB by QHB is equal to 1. The 1 and 1 cancels out. What are we left with? We are left with minus QCA by QHA is more than minus QCB by QHB, okay? And this is where we will use the assumption, the reference that we set, that QCA is equal to QCB. So we will use that assumption over here. So these two things can be removed from both sides, and they are positive numbers, they are modulus, so we can do that. Therefore, QHA is more than QHB, okay? So this looks like lots of algebra, but what we have done is something very, very simple. What we have said is that if you have two engines, both are taking some heat from a hot source. They are taking this heat and they are doing some amount of work. And they are dissipating some amount of heat into a cold sink. If the cold sink heat that is being dissipated is the same amount, and this process is doing more work than this process. So I'm trying to move my hand vigorously, hopefully you're seeing. And I'm not going to use left or right because on Zoom, the mirror can have a problem. So let's call this my watch process, and let's call this my iPad pencil process, right? So the watch is taking some heat from a hot source, doing some work out of it. The iPad pencil is taking some heat from the hot source, doing some work out of it, and they are both dissipating the same amount of heat to a cold sink. And you're saying that the work that you are getting out of the iPad, out of the watch, is more than the work you are getting out of the iPad pencil. Clearly, this means that the watch must be taking more heat than the iPad pencil, right? Because we know that W is equal to QH minus QC. So if QC is the same and the work is higher for one of them, the only way it can happen is that the heat that it is sucking out from the hot source is also higher. Does that make sense? Okay. And you could have done the same proof by not setting the cold sink to be same. You could have said, let's say we are taking the same amount of heat from the cold source. Then what would have happened? Just to make sure that we are all on the same page. I want someone to think and answer this for me. If for two engines, we had assumed, instead of the cold sink being same, if we had assumed that the amount of heat they were sucking in from the hot source was same, and process A had a higher efficiency than the process B, then which one would be dissipating less amount of heat to the cold sink, A or B? something in chat. A, can you explain, Rohan, why?
Yeah, can you hear me?
Yeah.
Yeah, basically it's the same argument, right? That if it's dissipating the same, if it's taking in the same heat, and the work done by A is more, then A is going to dissipate to the coal sink lesser.
Yeah, exactly. So if A was able to convert all of the heat into work, then it would be dissipating zero work, right? That's the idea. So since I have you, Rohan, what do you think about today's Nobel Prize? Isn't that related to Wendell Hill's research?
Yeah, it's about like ultra-fast laser pulses as well. Yeah.
So you must be very excited.
Yeah, it's pretty exciting. Yeah.
Yeah. Did you see about the Nobel Prize yesterday?
No, I didn't.
That one's very interesting. It went to two people for the mRNA vaccine, and both used to be at University of Pennsylvania. And the woman, Carolyn Krakow, she was denied tenure at UPenn back in the day. They fired her because,
Wow.
and also both of their papers were desk rejected from Nature and Science, and now they won Nobel Prize. So it has so many positive lessons and shitty things about academia that, so it's interesting. Tomorrow is chemistry. We'll see who gets it. Okay, good. So let's draw this visually. So what we are saying is that we have a hot source at TH, and we have a cold sink at TC. Okay, and we have.
Can I ask a question real quick?
Yes, please.
So we're assuming that QC is equal to QCA is equal to QCB, but we don't really know that. So how is it a valid proof if we're making that assumption?
That's the point. You have to assume one of the two things. When you are comparing something, when I compare, let's say, I want to compare Rohan and Lydia's athletic abilities. I want to compare who is a faster runner of the marathon. In order to do that, I would have to compare how much energy are you consuming, right? So a good comparison would be somehow Rohan has a magical way of consuming 50,000 calories a day. I don't know. Maybe Rohan has found some secret. Something is in the chat. He wishes. Well, you could do it, but it won't work, right? So if we want to compare it for the same energy input. So that's why I said would it make more intuitive sense if you thought about it? Efficiency of two engines for the same amount of heat that they are drawing from the hot source. Would that make more sense, Lydia?
I suppose they make the same amount of sense. I'm just like,
okay.
I don't know. I'm just confused on how we can set those equal to each other when we don't
Yeah,
know that they're
point. That's why I knew this happens. That's why I went slowly over it. So it's just a question of reference. If you leave those two things to be different, you cannot compare two thermodynamic engines. So the proof really applies for the same amount of dissipation. Otherwise, you will be, you have some suggestions, Rohan, from the undergrad. So it just won't make sense to compare two engines. Think about it again, okay? And when I'm back in class on Tuesday, if you're still unhappy with it, let's discuss more, okay?
So we're basically just making like a reference frame, right?
It's just a reference frame. It's exactly a reference.
Okay.
Just a reference, yeah, but it's a subtle point. So now we have engine A, and here we have engine B. Engine A is taking QH, and as I finish through the proof, you will see why it makes more sense. It makes the whole thing very elegant. And it is doing some work, WA. Engine B is taking some heat, QHB, and it is doing some work, WB. Engine A is dissipating, QC. Engine B is also dissipating QC, right? Because we have set both to be the same. Now we are going to do something very interesting. What we are going to do is, since we are thinking about reversible processes, we are going to run engine B in the opposite direction. It's reversible, right? So no one's stopping us from doing that. We want to reverse engine B. So this becomes, since Jock pointed out the uranium example, so this becomes something like Jock is run. So Jock eats a lot of food and then runs. And if he does it reversibly, we can do the opposite thing, right? We can instead of running, Jock can like anti-run and produce a lot of food. That would be crazy, right? But that's how reversible processes are. So we imagine that we are going to run B reversibly, everything in opposite. So now you have B, and instead of producing work, you are doing some work on the engine B, and it is taking some heat QC from the cold source, and it is putting some heat into the hot sink. Can anyone think of a practical realization of such a process B in green that I drew? You can just unmute and answer.
Wouldn't this end up making a perpetual motion machine, which is
That's
technically
why
not possible?
don't kill my suspense, Sanjana. Come on. But first tell me, Sanjana, since I have your attention, what is a practical realization of this process B running in reverse? Or anyone else? Yeah, go ahead.
I mean, does it mean that it violates something?
No, simpler. An equipment that looks like process B.
A refrigerator?
Or an AC, right? Refrigerator and AC are the same thing, right? A refrigerator, right? It takes some heat from somewhere that is cold and it dissipates the heat outside. So if you stand behind a refrigerator, it gets very hot. Same for an AC. It's taking heat from a cold source outside. Your refrigerator is better. Just stick with refrigerator, okay? Is that clear to everyone? The work done, W is the electrical energy we provide to it. Yes, exactly. Now you are doing some work to run the process. It's a refrigerator or whatever it is. So now if you forget about the process B in the middle and you just look at this process A running forward and this process B running backward, right? If you look at both of them, and this is where we get to what Sanjana said, there is something going on. What is the net effect on the cold sink? Process A is dumping QC into the cold sink, and process B is taking QC from the cold sink. And here we have to write QHB modulus. So the net effect is that you're doing nothing to the cold sink. If I draw this over here, I could draw a box. This is cold sink at TC. This is hot source at TH. And the net effect is that you have a process A, which is taking some heat, QHA. You have a process B, which is giving back some heat, QHB. And process A is doing work WA. And on process B, you have to do work WB. And nothing is being dissipated to the cold sink. Okay? It's like there is nothing here. Nothing is going on. Let's think of it one step further. What is the net effect of this? First of all, we need to remember which one is higher, WA or WB, which is higher. Which engine had higher efficiency, A or B? We started by saying eta A more than eta B, right? That's how our proof started. Therefore, WA must be higher than WB. And we also showed in equation number 4 that QHA is more than QHB, right? And equation 4 said that QHA is more than QHB. So given this, what is the net effect on the hot source? Process A is sucking some heat out, QHA. Process B is giving it some heat back, QHB. But overall, you are sucking some heat out of hot source, right? That is QHA minus QHB. And since this WA is more than WB, you can use some of this WA to run engine B, right? So you could use this work done by the engine A to generate the electric current that is needed to run engine B. So how will the full thing look like? It's going to look like, again, we draw a. So even though this proof is like just for Carnot's theorem, which you can remember the statement very easily, but I still like to go through the proof because I think it's elegant. So you have hot source at TH, and you have cold sink at TC. And the net effect is that you are taking QHA for process A. You use WB work out of this, WB out of WA. You do that much work to run the process B, which in turn gives back heat QHB to the hot source. And what is the net effect? Since A was more efficient, right? So A produced more work than was needed to run B. So the net effect is WA minus WB work is happening. This is very interesting. What we have just done is we are able to take heat, net heat, QHA minus QHB, which we know is positive. We just proved it in equation 4, out of hot source and produce work WA minus WB without any dissipation. This is what Sanjana said is a perpetual motion machine. This is a violation of the second law of thermodynamics, but I'm going to show you exactly how it violates one of the postulates, okay? Does anyone want to help me? Why is this situation a violation? Why is this a violation of one of Callan's postulates? How should I show this? And remember, everything is reversible. That's your hint. We are talking only about reversible engines. How should I proceed? You don't have to prove the whole thing. You can just give me the gist if it looks to you what is it that we should go after? Anyone? Your hint is entropy. What happens to the entropy of the full system? Hot source plus cold sink. Together they are isolated, right? Together all of this is isolated. And everything is reversible. If it's reversible and isolated, what do we expect delta S to be?
0.
Why? Because ds is equal to delta Q reversible by T, right? So reversible already showed up, and on top of that, you are saying it's isolated. Therefore, delta Q is equal to 0, and it's a reversible process, right? So this means that ds hot source plus ds cold sink should be 0 if the whole thing is happening reversibly. What is ds cold sink in this case? Same thing, delta Q reversible by temperature. What is delta Q for cold sink overall? It's 0, right? This is equal to 0. What is delta S hot source? That is QHA minus QHB divided by TH. That's a positive number, right? So delta S is positive, even though the whole process is being operated reversibly. And that's our contradiction. And that completes the proof. So it looks a lot of math, but intuitively you can see what it is we are saying here. We are saying if you were running two engines between the same hot source and the same cold sink, let's assume they are both dissipating the same amount of heat into the cold sink. Just for reference, you could have also talked about, let's assume they are both sucking the same amount of heat from the hot source. The proof would be similar. And I welcome you to go and try that proof at home if you want to gain confidence into this. So if we do this, we can say that, well, QC and QC is the same for both A and B. Let's run B reversibly. So it's actually sucking heat out of the cold sink. And A is giving that much heat into the cold sink, so it's easy for B to do that. So the net effect is that the cold sink is not getting any heat. Overall, the process looks like you are taking in QHA minus QHB heat amount of heat from the hot source, and you are producing WA minus WB work without doing any dissipation. this is a violation of the second law of thermodynamics. This is a violation of Callan's postulate because the whole thing is reversible. So ds for the whole system should be 0 for the whole hot source plus cold sink. But clearly here ds is positive. So it's not a reversible process. So the engines were not operating reversibly and you have a contradiction. So why did we do this proof? The main thing I want you to remember from this proof, if you can remember the proof, that's fantastic, but it's likely you will forget it. And I'm not talking about the course of this semester. I'm interested in you learning thermodynamics for the next 20 years. You will probably forget the proof. What you should not forget is Carnot's theorem, that if you are running an engine between a hot source at TH and a cold sink at TC, the maximum efficiency you can obtain is 1 minus TC by TH. And this applies to reversible or irreversible. This is a beautiful bound on what is the efficiency any process can have. Any questions? Shah, you don't have any questions?
No, I'm good.
Wow, am I in a dream? Okay, I will take that.
I have
Okay.
one
Yeah,
kind
go
of
ahead.
unrelated question, but
Yeah.
it's just out of curiosity. So, like in the diagram you have drawn at the top of this page, we are getting network WA minus WB, right? And what if we use that to maybe give power to another engine, WC, and we went on like this infinitely? Would we ever reach somewhere where
Oh,
the
you
difference
won't.
would become
You
zero?
won't. You won't. People have tried. You won't. You can try to. You won't. You cannot make a perpetual machine, but tying it to another perpetual machine.
No, what I mean to ask is eventually would we reach a point where the difference of the work would be zero?
You could. I mean, you could construct a process where the differences are so small. I think you will still have a violation. I would need to think about it, but you'd still have a violation. Yeah, you would still have a violation. Okay, good. So let's proceed further. Here, the most practical thing that you remembered is that you should remember is the Carnot efficiency. So this is known as Carnot efficiency. And you can also try to construct some other process. Here we did this isothermal, adiabatic. You could construct some other process and you would still find that the efficiency is, if the process is reversible, the efficiency must be the same, irrespective of how you carry out the process. It could be isochoric, isobaric, isochoric, isobaric. You could have a reversible process that looks in a pressure volume diagram like isobaric, isochoric, isobaric, isochoric, right? This rectangle that I drew over there, if it's reversible, it would have the same efficiency. I think that's beautiful, right? Because it's not obvious to me just by looking at this diagram, why should that reversible cycle have the same efficiency? You could go and actually calculate the algebra for it, and maybe I will give you a future problem or a midterm problem on something like that, and you will find it has the same efficiency. And Carnot cycle already tells you, well, it has to be the same efficiency. Okay, so this was kind of abstract. Maybe you enjoyed it, maybe you were like, ugh, but I think it's nice, and hopefully you will go back and read it and like it even more. Now we are getting to the more practical part of thermodynamics. Okay, so the way this semester proceeds is we set up our foundations, we become rigorous in the postulates we are going to use, as rigorous as we can be in a chemistry course. And then we gradually start getting into more and more applied things. So before I do that, I want to do a brief recap of one of the most important concepts which can be stated in few different equations. Okay, so I want you to help me along, okay, as I do this. So I want you to think about the value of ds for 4 different processes. The first one is an adiabatic reversible process. The second one is a reversible process, adiabatic or not. Third one is some process, generic process, which is spontaneous, which likes to go in the forward direction. And the fourth one is a generic process whose opposite is spontaneous. What can we say for DS in the first one?
0.
0, because it's adiabatic reversible. What can we say about DS in the second one? It won't be an equal to. That's your hint. Someone apart from Sanjana?
Q reversible over T.
Delta Q reversible over T, but an equal or more than?
More than.
Matt, think again.
Oh, sorry, 0.
Equal, right? Delta DS is equal to delta Q reversible by T. In third one, anyone wants to help me here? We have had Matt, Lydia, Sanjana, Rohan help, someone who hasn't spoken. And I already wrote the more than, so I made it easy for you. It will be delta Q by T. And DS more than delta Q by T means that the forward process is spontaneous. And if DS is less than delta Q by T, it means the backward process is spontaneous. Now let's look at it very carefully. S here means S of the system, right? This means S of the system. And Q in all of these, Q is heat being given to the system from the surrounding. So I imagine at this point, the first two look more familiar to you. I'm sure some of you, or maybe all of you, are slightly confused by the last two. Let me just give you an example of what the last one looks like. So let's say for these one, or for any of them, if you have a reaction, A plus B going to C, right? So the DS of the system in this case is SC minus SB minus SA. And let's say this reaction is happening in a beaker, and you gave some heat to the beaker, which is delta Q, okay? At temperature T. This is where your reaction is happening. So if you knew what is the amount of delta Q and what is the temperature, and if you found that SC minus SA plus SB is more than delta Q by T, that means the reaction will move towards the product stage. You will form more and more of C, right? So this means C forms. And if SC minus SA plus SB is less than delta Q by T, that means A plus B form, right? So that's why this is so important, because this is what sets up. Later we will see this story, the whole third, and you must have seen it in PChem undergrad also. This is what sets up the story of chemical equilibrium, right? So this is good, but there is a problem. We have to always worry about the heat given to the system. We cannot just talk about a reaction and say whether it likes to go from A to B or B to A. We always have to think about, well, how did you give heat to the system? How much heat did you give to the system? It's a bit bulky. Is there a way to remove heat completely from the picture and then talk about spontaneity? Can we do that? So we know, for example, that spontaneous change, by the way, in thermodynamics, spontaneous does not mean instantaneous, okay? So let me clarify, spontaneous is not equal to instantaneous. So someone asks you at the end of the semester, did you like 684? And you say, yes, I spontaneously liked it. That does not mean that you started taking it and the first class itself you liked it. That was instantaneous liked it. Spontaneous means that through the course of the semester, I kind of worked on you and gradually you started liking it. That is the lower energy configuration where you reach. Spontaneous means something that happens in the age of the infinite universe, in the limit of the infinite time. It doesn't tell us anything when will it happen. So we are talking about here, C will form, but there is no notion of time. Yeah, raise your, yeah, Anjali, go ahead.
I just have a question about, I mean, Okay, I know like we all know about spontaneity defined in terms of delta G. So isn't there like more than just an entropic component to
Oh yeah,
determine like
are
spontaneity?
you talking about delta G?
Yeah, so because
We are
here you're
getting to
just
free energy.
talking about,
That's exactly what we are doing now. We are getting into free energies very carefully.
but you're still using the word spontaneous to describe a process just based on looking at like the entropic components.
Yeah. So that is the most, exactly. So we will get to free energies like in today's class, but the whole point is spontaneous change is always defined as ds more than delta Q by T. What Anjali is doing by going to her PChem, superior PChem knowledge from undergrad is say, can't you define spontaneous change in terms of free energies? We are going to go there very rigorously, very carefully in just a moment, okay? So the problem with
I'm
this,
not like just saying that though, because I'm also asking like if
yeah,
you can define spontaneity just looking at entropy. Like if I just took the entropy of the process, like it might not actually be spontaneous.
it won't be because you have to think about delta Q by T. So just looking at ds of a process tells us nothing about spontaneity. Are you happy with that?
Sure, but is ds greater than dq over t equivalent to like delta G negative?
Absolutely. That's exactly what I'm going to,
Okay. Sorry.
that's exactly what I'm going to show.
Okay, I didn't see the feature.
Yeah, we are getting there. So
Excuse me.
ds, yeah, go ahead, Shah.
So you just said that delta S doesn't tell us anything about the spontaneity. What about the sign of it, if it's positive or negative?
Oh, I think that still works, but you have to be careful. So you are saying, well, what if delta Q is negative, right? It still works. This is robust to that. Yeah. So in general, just, yeah, good point of just looking at DS process, or actually I want to call it DS system, does not tell me anything about spontaneity unless I compare it to delta Q by T. And so far in thermodynamics, this is the only definition of spontaneous change. This is the arrow of time. This is our arrow of time. Time only moves forward, and this is what defines the arrow of time. However, if you were looking at a closed system where you have a system and you have surrounding, and the full thing is isolated, then delta Q of the system plus surrounding, that is zero, right? The full thing is insulated, nothing goes in. In this case, ds system plus ds surrounding is more than zero, becomes condition of spontaneous change. So in this case, we don't have to talk about delta Q system because it's an isolated system, right? So there is no need to worry about delta Q. So far, let me recap this. We have defined, we can think of spontaneity in at least two different ways. One is that ds total, which is ds system plus ds surrounding, is more than zero. This is messy. I have to calculate the entropy change of the surrounding. Who is going to do that? That's like, I don't know how to do that. It's terrible. If you have to look at a chemical reaction, you have to think about the whole universe in order to look at that. And that's messy. That's number one. Number two is ds system more than delta Q system at and whatever temperature the process happened at. It's a bit better. You don't have to worry about the surrounding. You just have to look at the heat that you took from the surrounding to the system. Turns out there are two other definitions for spontaneity, which apply in two particular conditions that are really powerful. In those two particular conditions, the definition for spontaneity actually reduces to only properties of the system. That's a remarkable result. At constant temperature and volume, or at constant temperature and pressure, these two sets of conditions give a special form to conditions to spontaneity. Turns out that if you have constant temperature and volume, the spontaneous change is the direction in which a particular state function A of the system becomes negative, where this A is defined as E minus Ts. So you can see why A is a state function, because E is a state function, the energy, T is a state variable, and S is a state function. So at constant temperature and volume, the A of the system should be negative. It does not matter what's going on in this system, whether you are pumping heat into it reversibly or irreversibly, whether it is isolated, whether it is isothermal. Well, it is isothermal, we assume T and V. The only thing you want is it should be isothermal and isochoric. If it's isothermal and isochoric, constant temperature and volume, then suddenly delta Q disappears. That's just like mind-blowing that it happens at constant temperature and volume. And at constant temperature and pressure, there exists another state function G, which is H minus Ts, that should become negative. And this is where thermodynamics really now starts to become more and more practical. We are gradually making it practical because temperature and volume are conditions we can control in a lab, right? We have a furnace. The furnace is coupled to some sort of heat source at a constant temperature. It is keeping the furnace at the same constant temperature, and the furnace otherwise is shut. It's a fixed volume. It cannot change its volume. That's condition number 3. Condition number 4 is a test tube. Again, you're keeping it at a beaker at room temperature, right? It is controlled to be at that same temperature through some heating source or some cooling source, and it's open to the atmosphere, so the pressure cannot change. So in these two cases, the condition for spontaneity becomes super simple, and I think this is awesome. And again, notice something that happened to the sign. For the first two, and by the way, 3 and 4 follow from 1 and 2. 3 and 4 are specific cases of 1 and 2. 1 and 2 are exactly equivalent, okay? 3, you cannot prove 1 from 3. You cannot prove 1 from 4, right? Because 1 is more generic. 1 applies to all processes, not just constant temperature and volume. Same for 2. 3 and 4 apply to very special type of processes. So let me write it down again on the next page. Condition for spontaneity can be expressed solely in terms of state function of the system with no need to think about delta Q. So it just doesn't matter what is the delta Q and whether the process not whether, but let me write it how the process is being carried out in two specific cases. So both cases impose some restriction on how the process is being carried out. You have to be either constant temperature or volume. Constant temperature or volume, the condition for spontaneity becomes dA system less than 0. And this is fantastic. You can just, A is a state function. Yeah, just one moment, Anjali. A is a state function. So if you have a chemical reaction that's going on from X to Y, you can just look at A of X and A of Y and you're done. I will come back to you in just a moment, where A is defined as E minus Ts, and this is known as Helmholtz free energy. And at constant temperature and pressure, the G system is negative, where G is equal to H minus Ts, and G is known as Gibbs free energy. Yeah, go ahead, Angel.
Oh, I didn't have anything.
Oh, you didn't? Okay. You were just
No,
like
no.
high-fiving or something.
Oh, I
was-
don't know why. Sorry.
No, it's okay. I assume it was a high five that you also got as excited about that such equations exist. I think it's amazing that you can do something like this only under these conditions, and other conditions it won't work. So what do we want to do next? We want to prove this, right? So let's prove this. Proof that this is really true. And the proof is quite simple. We will prove this and then we will stop for the day. Next time, or maybe do a little bit more. And next time, by the way, Thursday, there is no class. I'm very happy with the pace so far. And this is the last Zoom class I have to do. So I really, really am thankful to you all for bearing with me, because I don't want a substitute teacher necessarily. It doesn't help. It's best if I do it this way. By the way, I hope today's screen sharing was clearer than previous time, because yeah, I was able to figure out something. So we will do proof for this, and then we will start thinking about the natural variables for A and G, and then we will derive something which is known as Maxwell relations, and then we will see how A and G and H are actually Legendre transforms of each other. We will address the question that Venkat raised on Slack as to why does entropy maximization translate into energy minimization? And in this case, now you can already see it translates into free energy minimization also. So we will look at all these things carefully. And then once we do that, these two things allow us to think about phase diagrams, which is a cornerstone of thermodynamics. We will be drawing a lot of phase diagrams. We will be looking at phase diagrams of simple single component systems, multi-component systems. We will be looking at things like spinodal decomposition, phase separation. So if any of you is thinking everything is obvious so far, it will build up. At the end of this course, you will have a lot of tools. Some you have seen, some you have not seen, that you will find useful in research. So what do we want to do now? Let's prove the first one, which is at constant T and V, we want to show that D of A less than 0 is condition for spontaneous, or just spontaneous change or spontaneity. What is A? A we have defined as E minus Ts. So D of E minus Ts less than 0, right? This is what we want to show. So we are working in the opposite direction. In other words, dE minus TdS minus SDT less than 0. What can we say about SDT for this process? It's happening at constant temperature. So what is the value of SDT? It's 0, right? Is equal to 0, because we are talking about constant temperature and volume. So if someone tells you, and this is a problem that people who have not carefully taken thermodynamics make such mistakes, including professors, all the time. They look at a chemical reaction. There are so many papers where people just use Gibbs free energy for spontaneous change when their process is happening at constant temperature and volume. And it could be biochemists, it could be organic chemists. They completely forget that the free energy that you need to look at changes. And sometimes it's not happening at constant temperature volume or constant temperature pressure. Then you cannot use G or A. You have to really think about the whole Clausius inequality, that ds is more than delta Q reversible by T. So you have to be careful. And so, thermodynamics is few simple rules, but you have to be careful. So at constant T, this is going to be 0. So we have dE less than TdS or ds more than dE by T. What should I do now? Does anyone see? How do I prove that indeed this is the condition for spontaneity?
Expand dE into delta Q minus P external dV. And
you are saying
since
expand dE into
delta Q
first law of thermodynamics,
yeah,
right?
yeah.
Okay, Sarat, say with me. You have exactly the right idea. So Sarath is saying, write down dE is equal to delta Q minus
Minus
what?
P external dV, but at constant
Sarath?
volume,
It's constant volume. So what can I say about P external dV?
0.
Haha, there we go. Or ds is more than delta Q by T. This is the condition for spontaneity, right? ds more than delta Q by T is the arrow of time. So we just proved that T of A less than 0 is the same as ds more than delta Q by T at constant temperature and volume. You could have done the proof the opposite way also. You could have started from here and gone in this direction, and you would have gotten the same thing. So simple algebra, but it proves something very, very useful. Okay, let's try to prove the next one, and then we will stop for the day because we have covered a lot of ground. So this is page number 7. Now we want to show that dg less than 0 at constant T and P is spontaneity. So I said that for this one, we could have gone in the opposite direction. We could have done ds more than delta Q by T and start from there. So let me do the opposite direction for this one. And you'll see it's exactly the same proof. So we know that ds more than delta Q by T is our condition for spontaneity for any process. What can we say about this at constant? We are talking about constant pressure and temperature, right? So what can we say about delta Q at constant pressure? Your hint is don't worry about temperature at this point. If it's a constant pressure process, what happens to delta Q? Remember Cp? How did we define Cp? Heat capacity at constant pressure. It becomes delta H. And the difference that is not clear from what Rohan wrote in chat is that it becomes dH by T, right? H is a state function. It's a total derivative. Sorry, not equal to ds more than dH by T, right? Because it's a constant pressure process. So this happened due to it being constant pressure. We haven't used constant temperature. Or dH is less than TDS, right? It's a constant temperature process. So we can just add over here, or dH is less than TDS plus SDT, because dt is equal to 0 for constant temperature process, right? Or dH is less than d of Ts, or d of H minus Ts is less than 0, or dg is less than 0. So we did the same proof as we did for dA, but in the opposite direction at constant temperature and pressure. So let me summarize, and this is possibly the most important few equations in this semester. The first law and the integrated first law and second law are also very important. This is in the same category. So let me recap once again what we saw today. Spontaneous change is many ways of writing it. ds total is equal to ds system plus ds surrounding more than 0. This is spontaneous change, which is equivalent to saying ds system is more than delta Q system by temperature, right? Today we showed that at constant temperature and volume, dA system less than 0 is also condition for spontaneous change. Or if the process was happening at constant temperature and pressure, then dG system less than 0 is the condition for spontaneous change. But you have to remember dA applies only for constant temperature and volume, and dG applies only for constant temperature and pressure. So anytime you read a paper and someone says this reaction or this process is spontaneous because the free energy goes down, you have to say, hold on, which free energy, Helmholtz or Gibbs? And they tell you Gibbs. And you say, good. Now tell me, did you do your process under constant temperature and pressure? They say no. Then you tell them, well, then your paper is crap. It should be retracted, because you cannot talk about equilibrium coming from Gibbs, spontaneous change coming from Gibbs free energy, if the process is not temperature and pressure. So these 4 equations, which we proved, the first 2, this is Clausius inequality. You can see why this is very important. This is like base. We do so many things from it, and that's why I made you go through it in the homework also. And from this, we were able to show these 2. Okay, I will stop here. Any questions? Matt, any questions?
Nope, all good. Thank you.
Okay, thanks, Matt. Okay, so no class on Thursday, and use that time to go over the material. The homework is also big. Please solve it. Please solve it carefully. I would love to see everyone scoring 105 on 100 in this homework if possible. So take your time to work through it. Don't rush through the homework. Go through it carefully, especially the entropy problem, the Carnot cycle problem of drawing the process in different representations. That's not an easy problem. Work through it carefully, and then it will give you a lot of confidence into what we are doing. Apart from that, we will meet next Tuesday onwards in class. Okay, thank you, everyone. Have a nice day.
Thank you. Bye.